When we think and talk about multivariable functions, the idea of rate of change certainly comes up. How does one quantity vary with respect to another? Well, in particular, when we're dealing with multivariable functions, we want to, again, limit ourselves to only dealing with one allowable variable in the problem. So our question now becomes, how does the output change if you change one of the input variables while holding the other constant? Our obvious example is the situation in which we have the cost of renting a truck as a function of the number of days, D, that you rent it for, and the number of miles that you drive on it times 0.47. So let's ask a couple of questions to do a function reduction here and think about hey, what's going to happen when some of these things are held constant? Okay, well, if m is equal to 300, and we write our function as we have in the past, then we have this function can be rewritten as c of dnm. Let me get that up there real quick. So c of d comma m, and so we can do the reduction function by saying let's hold m equal to 300, and so in that case we're going to get let's see, 0.47 times 300, which is going to give us 47 times 3, or 141, I believe. So 1999d plus $141 for the 300 miles driven. Okay, so now we can analyze this and we can say, okay, well, if you look at cost versus the number of days that you have it for, with the vertical intercept of 141, we have a constant rate of change in the cost. So we can say that cost increases at a rate of $19.99 per 1 day. Okay, so that's the idea of rate of change already incorporated in there. That's, in other words, the slope of the line. The slope of the line here is going to be slope equals 1999. Okay, well, how does that differ if I fix m to be 500? Well, if I fix m to be 500, then all I'm going to do differently here is allow in place of the 300, I'm going to have 500. So c of d comma 500 is going to be 1999d plus 47 cents times 300. Sorry, 500 in this case. Okay, well, 47 times 5, don't exactly know what that's going to come out to be off the top of my head. But again, when we plot d versus cost, we're going to get a linear function. The only factor affecting the cost now is going to be the number of days that you own it for. And again, the slope of this line is 1999. Same idea here goes for 600. So the relationship between cost and days, so the relationship between cost and days is such that cost increases by $19.99 per day. Okay, that's a constant rate of change. So not much going on there. And in fact, you didn't even have to tell me that what m was equal to. Regardless of what m was equal to, in this case, the rate of cost change was exactly the same. That's not always necessarily the case. But before we proceed any further, what we're really referring to is the idea of delta y delta x versus dy dx. So what's the difference? Well, we're talking average rate of change versus instantaneous rate of change. And we're really, in other words, the derivative. So we're going to be using the derivative here, and this can more easily be thought of as, okay, let me draw a function here. And let me just say that this is the horizontal and vertical components of a roller coaster that you're looking at from the side. Okay, so it looks like this, right? So between any 2 points, let's say this point and this point right over here, if you're trying to explain to somebody how steep this is, and you say, well, you know, when I was 10 feet away from the start of the ride, I was 20 feet off the ground, and then at 30 seconds, I was only 4 feet off the ground. And so here's what happened with respect to the roller coaster. Well, that means somebody might interpret that as saying, well, you dropped 16 feet in 20 seconds. Extremely boring. or excuse me, you dropped the grade of this fall was 16 feet vertically for 20 feet horizontally. Well, that doesn't seem like very much, right? Because the average rate of change is the idea that we're ignoring everything that happens in between. But in reality, if you look at, so this might be delta y, delta x, but in reality, what I want to explain to somebody is maybe the drop of the roller coaster itself. So right here, in fact, if I looked at the slope, or if I would looked at, if this were the cart that you're in, and you were really at this point probably thinking, oh my gosh, this is maybe, and I don't know what the grades of roller coasters are per se, but the idea that at this one instant, you kind of get a sense of, well, I'm going down really quickly. Well, that is still a change in y with respect to a change in x, except it's instantaneous. And a lot of times mathematically, we just think about that as, okay, what's the slope of the tangent line that just touches that point right there? That gives us a better idea of what's happening at that instant. Okay, so quick differentiation there between the two, no pun intended. So let's do a quick review of derivative rules. We won't use these in excess as to the point you might have used them in a calculus class, but we'll just review a couple of them. So the constant rule, okay, well, first of all, a derivative is just a slope. It's just a rate of change. So although these rules look fancy, if I were to tell you, and by the way, we'll use a to represent a constant and x to represent a variable. Okay, so if I take the derivative of a constant, I get 0. That's not a fact to memorize. That's actually pretty intuitive. If I think about a as a function with respect to x, if this is the x-axis and this is the function y equals a, and I ask you what's the slope of this? Well, the slope is 0. So that's where the constant rule doesn't really need memorization. It's not really as much of a rule as it is just putting something symbolic onto something that we could justify intuitively. Now, the power rule is one of those ones where it becomes a little less intuitive, but if we have x raised to a constant power, x squared, x cubed, x to the fourth, then it's the derivative of that function is, most people think about this as the exponent comes down, you subtract 1 from the power. Now, again, a is a constant, that's a number, so the variable is in the base. This is called the power rule because we're dealing with power functions. The most obvious case of this would be looking at a graph of either like a linear or quadratic function. So if you looked at a linear function, then something like, whoops, back up here. I don't know what's going on. Okay, there we are. In this case, we have, get my ink color here before I proceed to write, maybe something like y equals 3x to the first. Okay, well, this is a power function, right? Because the power in this case is really x to the first power. Okay, well, the coefficient doesn't really affect this, the variable, it just scales it by a factor of 3. So if I take the derivative of this, well, that means I drop the power down. Okay, well, 3 times 1 times x to the 1 minus 1. Well, 1 minus 1 is 0. 3 times 1 is 3. So I get 3x to the 0, and x to the 0 is 1. So I get y prime is equal to 3. Another way to write the derivative is y prime, if you recall. Instead of saying dy dx, I could also say y prime. So dy dx is the same thing as y prime. Specifically, you probably want to say y prime of x to indicate what your input variable is called, but in any case. So you don't really need a power rule here, but this power rule does work because we know that the slope of a linear function is a constant 3. Yeah, it's a constant derivative or constant slope of 3. But in less obvious cases, like if I give you y equals 10x squared, its derivative is actually 2 times 10 is 20, x to the 2 minus 1 is 1. And if y is equal to x to the 100th, probably can't even visualize what that function looks like, that is 100 times x to the 99th. Okay, so power rule is the first rule we usually learn in a calculus class, maybe aside from the constant rule. And now the exponential rule. Okay, so it's really important to distinguish between these two notations. X to the a and a to the x are very different. You can't just ignore that little detail. You can't just say, oh, they both have a base and a power. In this case, an exponential function is one that has the constant in the base. So examples of that would include functions like y equals e to the x. Okay, y equals e to the x occurs when we're dealing with continuous growth. And so that means y prime would equal the, let's see, the natural log of a. Well, what is a? A, from this template, tells me that a is the base. Okay, e is a constant. E is approximately 2.71828 or something like that. And just like pi, it's a number. So natural log of e in this case times e to the x, according to what the exponential rule tells me. Now the natural log of e is if you type that into your calculator, is 1. So the easiest derivative to remember for exponential is y equals e to the x and y prime equals e to the x, or dy dx equals e to the x. Okay, we could also write something like y equals 3 to the x, and its derivative would be the natural log of the base times the base to the x power. Or I could even have maybe something like 10 times 1.2 to the x power. Well, the coefficient, if you think about it as when I take a derivative, the coefficient doesn't really affect the rate of change of the variable component. So we get the natural log of 1.2 times 1.2 to the x. So the only time the derivative of a constant is 0 is when it's exclusively a constant function. In other words, you're dealing with a function that is a horizontal line. 10 times 1.2 to the x is not a horizontal line. So if you just said, oh, the derivative of 10 is 0, and then I take the derivative of 1.2 to the x, you're going to end up getting y prime equals 0. That doesn't make sense because exponential functions grow exponentially or decay exponentially. So that's the exponential rule in a nutshell. Logarithmic rule, fairly easy to work with. It says that the derivative of the natural log of x equals 1 over x. Okay, so that is the logarithmic rule. Not much there. Now we'll do kind of product rule, quotient rule, chain rule, all that a little bit later on. But for now, we're good. So we'll stop with those rules and actually try to apply this to multivariable functions. So how does this apply? Well, in multivariable functions, we have what's called the partial derivative. And why do we call it partial? Well, it's because we have multiple input variables. So when we take a derivative of a multivariable function, it's only with respect to one variable, treating everything else as constant. So we specify in the derivative which input variable is allowed to vary, holding all other things constant. So technically, you can, instead of writing even dy dx when you're dealing with single variable functions, dy dx, some people will write it using the partial notation, which kind of looks like a backwards 6 almost. So you can still read it. So usually people will say the partial of y with respect to x. So exactly the same thing. These things are exactly equivalent, except the partial notation is typically used when you have more than one input variable. Like instead of just having x, you have x and z as input variables. Okay, so the notation again is we just say the partial of y with respect to x. You can still say derivative of y with respect to x. It means the same thing. So the reason we like that, we use that notation differently is like if you have z of xy, where z is the output variable, x and y are your input variables, then partial of z with respect to y means we are taking the derivative of z, z is the function, we're treating y as a variable and x as a constant. Okay, so if you have a multivariable function, down here you specify in the denominator of this differential which of the variables is going to be constant, which one is going to be variable, which one is going to be variable, and which one is going to be held constant. One last distinguishing feature here, another way to write the partial derivative. So we don't actually use prime notation. We don't want to write z prime of xy for the main reason because, okay, which one's, that's the derivative of z, which one's the variable, which one's the constant. That's confusing notation. We don't want to use that when we're dealing with multivariable functions. So we have this notation, the partial of z with respect to y, or you can actually write z, and then in the subscript you can say the derivative z, take the derivative of z with respect to y, treating x as a constant. So these notations are the same in multivariable calculus. Okay, so in the next step, we're going to actually look at finding the partial derivatives, going back to our cost function, and what we find will not be a surprise. We'll go ahead and stop this video here and progress in part 2 to actually do some partial derivatives for multivariable functions. You'll find that this isn't it's intimidating, but it's not as bad as it looks. So we'll see you in the next video.